Before getting into more details about this specific work, I just want to give a more broad overview and motivations for my research, for this work in particular, and my research more in general. So even though this talk is going to sound more like a cosmology talk, my background is as a particle phenomenologist, and my research is driven by the question of how can we learn more and how can we discover some signatures of physical phenomena beyond the standard model. So as you know, we have very strong experimental evidence from astrophysics and cosmology that the particles in the standard model only cannot account for the total energy budget of the universe. And therefore, I think this is one of the strongest evidence that we have that physics beyond the standard model must be there. And in order to tackle this problem, I think one way to proceed is in these two steps. As particle phenomenologists, we should identify the theories that are the best, well-motivated extensions of the standard model, those that are compatible with all existing observations and that are predictive and lead to some striking observational signatures. And then moving to the observations, we should try to take advantage of all the experiments that we have from laboratory, particle colliders, but also telescopes and space missions in order to extract as much information as possible from these measurements to learn more about new physics. So this is the spirit that has been driving my research. And because we don't really know at the moment what are the best targets and where new physics can be, either in terms of masses or couplings, I think the right approach is to follow multiple directions. So from the theory side, I've studied, for example, dark matter candidates that are thermal relics from the early universe, in particular focusing on extensions of the weakly interactive massive particle, extending to masses below the weak scales and studying the different phenomenology of this type of models. From the observational side, I think one important very attractive probe of new physics and dark matter in particular is through their gravitational effects only. So I've developed, together with my collaboration, some new strategies to search for imprints of dark matter substructures in our galaxy through their gravitational lensing effects. And we develop an analysis using data from the Gaia satellite. Another very interesting phenomenon that, again, relies only on gravitational interactions of new physics, and in particular, new ultralight particles, is the phenomenon of black hole superradiance. And I've studied the particular case of vector superradiance, pointing out that when additional couplings are there, then this phenomenon can lead to very striking observational signatures. And based on this proposal, we're currently working on a search for new ultralight vectors with members of the LIGO, Virgo, and Caira collaboration to search for continuous gravitational wave emissions. So my most recent work has mostly focused on astrophysical and cosmological probes of new physics, but in the past, I've also worked on new physics searches at colliders, and in particular, in cases in which new particles that are too heavy to be directly produced at the LHC can still leave some imprints in the shapes of the kinematic distributions that we measure at colliders. So I just wanted to mention these other things that I'm excited about, and because I don't have a chance to visit in person, so I cannot chat with you in the hallway or over lunch, I would be happy to discuss more about this. So feel free to ask me at the end or send me an email also later. And I don't think there is one particular right strategy. So as I said, I think it's important to follow multiple approaches in the search for new physics. And today I'm going to focus on one particular probe for new ultralight particles through cosmological observations. And the particles that we want to target are new axion-light particles. So let's start from the theory. As probably most of you know, axion-like or axions or axion-like particles are pseudoscalar particles that arise in several extensions of the standard model. They have first been suggested more than 40 years ago as a solution to the strong CP problem. So they help explaining why the strong interaction of the standard model seems to be conserving CP. And more recently, it has also been pointed out how in some string theory scenarios, several axion fields, so beyond the only QCD axion, can arise with different masses and interaction strengths. Very interestingly, it has also been noted 40 years ago that axions can be a dark matter candidate. So through the mechanism of axion misalignment, they can make up the entire dark matter abundance. And more recently, other type of mechanisms, including pre-inflationary and post-inflationary scenarios, have been investigated in details. Although for the rest of my talk, I'm not going to require the axion to be the dark matter. I'm just going to ask for this particle to be present in the theory. An important point here is we're going to focus on ultralight axions. So I just want to remind you that these particles usually arise as Goldstone bosons. Their mass is protected by an approximate shift symmetry, and so they can naturally be light. And indeed, we're going to focus on, as I will show in the next slide, very small masses. And then finally, very importantly, if you want to look for observational imprints of these particles, it is nice if they couple to the standard model particles. And here I'm going to focus on this coupling of axions with the standard model photons. So here I'm just going to parameterize this coupling with a dimension-full parameter GA gamma gamma that in a specific theory can be related to a symmetry breaking scale, for example, but we're just going to take it as a free parameter. And this operator couples the axion field to electric and magnetic fields in a standard model. So it is a coupling of the axion to two photons. So this is the typical parameter space for axions that couple to photons. You see here coupling versus mass. From that, I borrowed this from these very nice online repositories that has a collection of all the existing searches for axion-like particles. So in red, you see a collection of laboratory searches. The most relevant for us is the CAST axion helioscope that is looking for signals due to axions that are produced in the sun that then travel all the way to the detector and within a large background magnetic field convert into photons. So they try to measure these photons. And then in green, there is a large collection of astrophysical different kind of astrophysical probes of axion-like particles that couple to photons. Here, what I want to point out in this talk is that cosmology can help to complement these searches, in particular for axion around 10 to the minus 12 eV. And for context, just to compare with the masses of the particles that we know in the standard models, here we're sitting at more than 10 orders of magnitude below the masses that at least some of the neutrino states might have to satisfy observations from neutrino oscillation experiments and cosmology. And if we want to look at even the lightest charged particles, a particle in the standard model, this is even 6 orders of magnitude heavier. So we're really talking about very light new fields. And you might notice from this plot already that when you go to smaller masses, astrophysical probes are typically more powerful. And one naive way to understand this is that usually when you go to small masses, the Compton wavelengths of these fields become very large. And so typically the effect of these particles decouples from the laboratory setups, which are on much smaller length scales. So it is usually advantageous to use astrophysical and cosmological probes that instead provide us with macroscopic length scales. And just one comment, I'm going to use the word axion in the rest of the talk, but remember, I'm not talking about the QCD axion, which has a specific relation between the coupling and the mass that is represented by a line not shown in this plot. And for small masses considered here, sits well below the couplings that we can probe currently experimentally. So this is the outline of the talk. Please feel free to interrupt at any time with questions or comments. I think for a Zoom talk, this is particularly encouraged so that you don't miss any part that if it's not clear, please ask me. So first, I'm going to explain what are CMB secondary anisotropies, that is the observable we want to use to probe axions, and then how axions can induce these anisotropies through photon conversion into axions inside halos. Later, the third part is going to become slightly more technical. I'm going to explain in detail how we compute the signal and how we compute the temperature and polarization two-point function and three-point functions. And finally, I will show the results with our projections and outline future directions. So let's start from CMB secondaries. The backlight, the photons that we're using here are coming all the way from the early universe, and we've measured these photons very precisely. Back in the 90s, Kobe was able to measure the spectrum of the CMB photons very well, and find that it was actually following very well just a blackbody spectrum. And it is still from Kobe the best measurement of the average blackbody spectrum of the CMB photons on the sky. Later in the 2000s, with satellites like WMAP and later Planck, but also ground-based telescopes like ACT in Chile, we've been able to measure fluctuations on top of this average blackbody temperature. And usually these results are presented in terms of power spectra, as the plot from Planck that is shown here. So the information here is that what they measure is the temperature difference between 2 points at a given angular separation on the sky. And it is usually given in harmonic space. So here, lower L corresponds to larger angular scales, while a smaller L corresponds to smaller and smaller angular resolutions. And the power spectrum that you see here is coming from perturbations that are of primordial origin and that can be explained, for example, in theories of inflations. And these have been very accurately measured by Planck and, as I was saying, other ground-based telescopes. However, on top of this, these photons that are coming from the early universe, they travel all the way to us, and they interact with a lot of stuff on the way. And in particular, the late universe is very far from homogeneous and isotropic. It has formed all these structures that are clustered and not distributed in an isotropic way. And so interactions with these structures in the late universe lead to additional anisotropies that are what we refer to as secondaries. And there are many effects in the standard model that induce these secondary anisotropies. The most familiar example probably being CMB lensing, that is due to the gravitational interaction of CMB photons with gravitationally bound objects, halos in the late universe. But there are also secondaries due to interaction with charged particles. For example, Thomson scattering leads to screening of the CMB, and then there are also Sanae-Zeldovich effects that are sensitive to the velocity of these charged particles, either through their high temperature or their bulk motion. And these secondary anisotropies have been measured. So I think it is interesting to ask ourselves, what about new physics? Is there any new physics effect that can lead to secondary anisotropies? And here I'm going to present one example, which is due to the CMB photon conversion into axions in the background of the magnetic field of halos. However, this is only one example. A very similar effect happens for new vector fields like dark photons, and there could be other scenarios too. So I think this is a very interesting question to ask. What kind of new physics can we test through CMB secondaries? And the reason why it's interesting to ask this question now is that future CMB experiments are expected to improve, in particular, at small angular resolution. So they're going to have higher and better sensitivity at high angular resolution, whereas where CMB secondaries manifest, because they are intrinsically related to the small angular scales of structures on the sky. And this will happen with telescopes like Simon observatories and more futuristic CMB S4 that are all partially based, at least partially based in Chile. But even current experiments like the Atacama Cosmology Telescope that is supposed to have a new data release later this year, it's going to improve compared to Planck, particularly at high multiples, so small angular scales. So they cover a smaller portion of the sky, but they have a better angular resolution. So if there are no questions so far, I can move on to describe how are axions inducing these secondary anisotropies. So as I said, we want to look at the conversion of CMB photons into axions, and this happens when we have an external magnetic field. So when we can replace one of these photon legs with an external magnetic field, then this is equivalent to a mixing between axions and photons. And very similarly to the mass mixing between neutrinos, this mixing leads to oscillation between photons and axions. And parametrically, the probability for this conversion is obviously proportional to the coupling squared and the strength of the magnetic field squared. And then by dimensional analysis, there must be some relevant length scale squared. So just by looking at this formula, we can immediately see that compare how large is this effect, either in a laboratory environment or in an astrophysical environment. So in a laboratory, usually we can set up magnetic fields of the order of Tesla for a length scale of centimeters or meters, while in an astrophysical environment, we're of course dealing with much smaller magnetic fields, but these can be coherent over long macroscopic length scales. So even though we're suppressed by the small magnetic field, we can still gain by several orders of magnitude thanks to the large length scales. So now, if this conversion can be, for the CMB photons, can be highly anisotropic, and this is due to the fact that photons travel through an ionized medium, which means that they acquire an effective plasma mass. And the square of this plasma mass, it's simply proportional to the number density of charged particles in the medium. So similarly to neutrinos, medium effects are important and need to be taken into account. So when this plasma mass matches exactly the axion mass, then the conversion probability before and after the resonance is negligible, and we can simply compute the conversion as the probability, the oscillation probability at resonance, which depends on the profile of this plasma mass, so the profile of the number density of electrons. And the CMB photons travel through a long distance, and they cross plasmas with different densities. And here I'm in particular looking at scanning of this plasma mass within structures, so within virialized halos. So here I'm showing the density, number density as a function of distance from the halo center for a Milky Way-like halo. Within the halo, we know that there is a profile for the dark matter, can be, for example, an NFW profile shown in blue. And there is also similarly a profile for the gas, for the charged particles within the halo, shown here in orange. And so for a given axion mass, the resonance conversion can be met at some distance from the halo center. So how does this look like on the sky? We're facing, imagine what we're looking in some line of sight, and this trajectory crosses a halo. Then at some distance from the halo center, at least within the approximation of a spherically symmetric halo, the resonance condition will be met here along this green line. And a typical trajectory crosses this resonance radius twice. So importantly, as I already mentioned, this conversion probability depends on the halo density profile. So this means that we will get a characteristic angular scale dependence. And also, it is proportional to the photon frequency. And this is very important because it allows us to distinguish the small signal coming from the axions from some standard model effect that does not have a frequency dependence, and therefore it preserves the CMB blackbody spectrum. And I will come back to this point later. So what happens is that, okay, we have all these photons, they come, they cross halos, and they disappear by converting them into axions. And this, of course, happens for many trajectories. We can compute integrating over all the halos using some halo mass function. We can sum up the contribution from all the halos, and we can compute how many photons disappear across all the blackbody spectrum. And what we find is that we expect a distortion in the blackbody spectrum that is larger at higher frequencies. So one naive thing we could do is we can compute this distortion and then face it with the precise measurements from the COBE satellite, and requiring the axion coupling to be small enough for this deviation to be compatible with the observations. And if we do this, we get that we can only exclude fairly large couplings of the axions that sit well within the region that is already excluded, robustly excluded by the CAST helioscope. But if we just do this, we haven't relied on the most interesting feature of the signal, which is that it is related to the location of structures, and halos are highly anisotropic. So it is more likely to have halos that are clustered together. And wherever we have a galaxy, of course, this is just a pictorial representation, it's not on scale, but just to give you an idea, wherever we have a galaxy on the sky, we expect photons to disappear. So if we look now at the CMB temperature map, we expect those points to be colder because they have less photons. And very nicely, we can correlate the CMB temperature map together with a map of galaxy over densities, because we know that the two signals are highly correlated. And this is precisely what we want to do. Oh, and finally, also, we want to rely on this frequency dependence of the signal. So Planck, as well as most of the CMB observatories, they measure CMB temperature maps in different frequency channels. And we expect these spots to be darker, bluer, in the highest frequency channels, of course. And so by combining the maps at different frequency properly, we can maximize further the signal to noise ratio. Okay, very nice. This is the idea. That's what we want to do. I just haven't said anything so far about an important detail that we need in order to compute the magnitude of the signal, which is the magnetic field inside the halos. So we have some evidence observationally that virialized halos have magnetic fields not only in the galactic disk, but also in the ambient halos, for example, from the Milky Way, or even from Faraday rotation observations of extragalactic magnetic fields. But we don't have enough observations to really have a robust prediction of what the magnitude of these fields is for all the halos and at all the redshifts. So for our purposes, what we do is that we rely on results from cosmological simulations that are magnetohydrodynamical simulations, meaning that they evolve the plasma of charged particles and magnetized plasma from the galactic disk. They trace its ejection from the disk out in the halo, and they find that at some redshift, roughly below redshift of 2, the magnetic field within the circumgalactic medium saturates to approximately a constant value. And the authors of these two papers that belong to the Auriga collaboration, they provide us with numerical fits to their simulation of the magnetic field profiles as a function of the distance from the halo center. And roughly these are of the order of 0.1 microgauss and are larger for heavier halos. So this is what we use. And now more recently, together with our collaborators at Columbia University, we're also validating these results together with other simulations from Illustris DNG. And Sam Goldstein here, the student working in this project, has so far been able to verify that there is good agreement between Auriga and Illustris, shown here by the red dots, while the black lines represents the Auriga results. So we're confident that at least on average, these predictions for the magnetic field should be somewhat robust. And remember, we're not looking at one individual halo, we're looking at statistically average quantities. So even though the modeling might not be right for one specific halo, on average, it should be somewhat robust. Good. So these are the ingredients, and now we can finally actually compute the signal.
Cristina, can I interrupt you? So I have a question, because so you expect the anisotropies to be small anyway, because we know that to a very good degree the CMB spectrum is rather isotropic. So I think that a crucial point in this discussion is the determination of the uncertainties related with the magnetic field, because if those uncertainties are sufficiently large, then you might get a result which is much larger. Your result, if the uncertainty on the magnetic field is too large, your predictions for the anisotropies will be to a certain degree not reliable. And I see that in this plot that you showed in the previous slide, you have error bars, but as far as I understood, these magnetic fields are produced or are deduced from embodied simulations, right?
Yes.
So from where those error bars come from then?
Yeah. So these are very preliminary results that Sam produced very recently, and we haven't discussed about it in too many details yet, but I assume these are just, given that they are larger for heavier halos, these are just some, because you have a limited number of halos that are heavier. So these are just from the simulations, you average and you have some variance. Just like if you could do infinite simulations and you have an infinitely large sample, you wouldn't have these error bars. So I think these are just statistical error bars. Of course, there could be systematics due to the way that the simulations are done. If some of the physics is not captured correctly, those I think would be more concerning. And yes, you're definitely right. The magnitude of our signal is proportional to the magnitude of the magnetic field. So an uncertainty on the magnetic field directly converts into an uncertainty on the size of the anisotropies. And that's why it would be much nicer, for example, if we could have more observations, like actual measurements of the magnetic field in halos, then we could rely on those to predict the signal. Yeah, I don't really know how to quantify those uncertainties. I wouldn't expect them to be orders of magnitude off, because the simulations do agree with existing observations from Faraday rotations. So I don't think they will be orders of magnitude off. And also, just to keep in mind that most astrophysical searches for axions do rely on background magnetic fields. So they are all somewhat affected by this kind of uncertainties, unfortunately.
Yeah, no, my point is that at the end, one should take into account that the magnetic field, comes along with an error bar.
Yes.
So at the end, how reliable the predictions are depends on how large that error bar is, or how much you have under control those errors, right?
Yes.
As well as you have there a halo dependence as well.
Yes.
So how much the prediction depends on the halo is also another question that might be, that one has to take into one has to bear in mind, right? So one has to be sure that one has under control those uncertainties, because at the end you will be calculating stuff, that involve error bars. Those error bars, they will propagate through the calculation. So it might be that the prediction, comes along with a huge error bar. So how reliable is the prediction at the end? That's the question, right?
Yes, I agree with that. So for our current work in the plots that I show you later, we didn't show those error bars, but currently we're also working on actually doing the analysis with Planck data. And I think for the actual bound that we're planning to derive on Axion, we're going to try to include some sort of uncertainties due to this effect. So.
Okay, thank you.
Yeah, I definitely agree. Great, so thanks for the question. So let's going to try to go into more details on how to compute this signal. An interesting feature of this Axion conversion is that due to angular momentum and parity conservation, not all the components of the magnetic field contribute to the conversion, but only the components that lay in the plane perpendicular to the line of sight contribute, and also each polarization component of the photons will convert accordingly to the magnetic field component along that direction. So we have to take this into account when we compute the Axion-induced reduction of the photon intensity and polarization. So for the intensity, the combination of magnetic field component that enters is just the sum of the square of the two direction in the perpendicular to the line of sight. While for the polarization, in terms of the usual Stokes parameters, Q and U, this is the combination that enters. And then this is in terms of intensities, but usually for CMB quantities, everything is given in units of brightness temperature, so just in units of the temperature, the blackbody monopole temperature. So from these equations, you see that because the magnetic field doesn't have the same direction everywhere, and it's actually changing direction randomly in different points of the sky, when we're summing over many different points, for the temperature field, this combination is always positive, meaning that the Axion-induced temperature the average axion-induced temperature is always negative, so it's a screening effect. But for the polarization, it can be sometimes positive and sometimes negative. So when we add up all these random signs, we just get 0 for the 1-point function, okay? However, we can now go to higher point functions. So let's go to 2-point functions, correlations, autocorrelation of CMB fields. So we can compute these higher point functions in a framework that is known as the Halo model, and it's a framework that is commonly used in cosmology to compute other type of CMB secondary anisotropies like Thomson screening, SZ effects, and so on. And these framework tell us that there are 2 leading contributions to the 2-point function. One is what is known as the one halo term. So for 2 points, N1 and N2, that fall within the same halo. So this one halo term is sensitive to the small scale shape of the halo. And it will be sensitive, therefore, to the mass of the axion, because heavier axions convert farther in the halo, and lighter axions farther out, where we have lower numbers and densities of electrons. And then there is a 2 halo term, which is instead considering trajectories that are crossing 2 different halos. And this is sensitive to the clustering of structures. So the fact that halos are formed from matter perturbations, and so these will be proportional to the matter power spectrum. And what we found from our calculation is that usually the one halo term dominates the signal to noise ratio. So we're dominated by the signal at small angular scales. What about polarization? So as I said, the average polarization is 0, but there is a non-zero correlation for points that are very close to each other and that they fall within the same magnetic field domain. Meaning that we're looking at 2 line of sights that are within the coherence length of the magnetic field. Unfortunately, for this polarization signal, there is an additional uncertainty coming from the magnetic field that is precisely this unknown coherence length of the magnetic field, in addition to what the uncertainty of the magnitude that we were discussing before. So because this is not known, not even accessible by the numerical simulations, we are parameterizing this by a free parameter that we fix to a physical scale. And then for each halo, it will depend, of course, also on the distance to the halo. So it converts to an angular scale. And again, because magnetic fields are randomly oriented in different halos, there is no 2 halo term. So these are what the CMB autocorrelation power spectra look like, in black for the temperature and in blue for the polarization fields. Importantly, because of this random orientation of the fields, the signal in the EE correlation is the same as in BB. And there is no E and B cross correlation, contrary to other effects like lensing. So here you see that the temperature receives a contribution also from larger scales, while the polarization doesn't, because there is no 2 halo term. The polarization is mostly like a shot noise signal, and so it's roughly constant as a function of angular scale. And as I said, the magnitude depends on the choice of this magnetic field domain size, and it is more suppressed for smaller coherence lengths. And we don't expect the magnetic field to be coherent over very large physical scales, and typically these will be below the maximum angular resolution of our telescopes. Great. So this was regarding only CMB-only autocorrelations. But as I said, the signal is highly correlated with halos. And therefore, if we have a tracer of halos, for example, lensing or a galaxy map, we can use it in order to cross-correlate the CMB temperature map, for example, with this tracer, and these are expected to have a non-zero correlation. So for the temperature field, the leading order non-vanishing is just a 2-point function, the cross-correlation. Very similarly, it has a 1 halo term and a 2 halo term. It looks roughly like this. Here, this is a busy plot showing the power spectrum in the cross-correlation. The colors correspond to axions with different masses, all for a given axion photon coupling. You see that at small l, large scales, roughly they have the same shape. And then as we go to smaller scales, the shape changes. That's due to the fact that at the small scales, the 1 halo term dominates, and this is sensitive to where within the halo the conversion is happening. And the black curve here corresponds to the galaxy autocorrelation that essentially roughly give us the level of noise that we need to compare with. And don't worry about the difference between the two curves. This is just a different sample of galaxies. Okay, so these are our theoretical predictions for the size of the signal. Oh, and yes, there is also correlation that we can do for the polarization fields, but because the average polarization vanishes, we need to go to a higher point function. So we really need to consider the 3-point function, the bispectrum, with 2 insertion of the polarization fields and 1 insertion of the galaxy fields. And this similarly has a 1 halo and 2 halo term with 3 points in the same halos, or 2 points in 1 halo and 1 point in a different halo. So we use all these observables to make projections. And to make projections, we really want to, of course, compare the size of the signal with the noise level. So let me say a few words on what is the noise that we're competing with. First of all, in order to reduce the level of noise, we use this powerful technique that is very commonly used in cosmology to reduce foreground contamination, for example, which is known as the ILC, and essentially consists in weighting different maps appropriately in order to minimize the variance with respect to a specific frequency scaling, which is the frequency scaling of the signal that is known in the case of the axion signal. And these allow us to reduce the level of noise that we're comparing the signal with for the case, for example, of temperature autocorrelations from the black curve, which is the primordial CMB power spectrum, down to the blue curve. So essentially what the ILC is doing is that it takes measurements from different frequency channels, it uses them to remove the primordial CMB, and then you're essentially just left with instrumental noise, which is shown here by the dotted lines, colored lines, which corresponds to the different frequency channels. So now a signal is observable if it sits above this blue noise level curve. So here I'm showing an example signal for a given axion mass and coupling. And you see different curves just showing separately the 1 halo and 2 halo term. So you see that the signal to noise ratio is maximized at large L, small angular scales. So now we can write summing over all the L modes. The signal to noise ratio is just simply given by the signal squared over the noise, the blue curve squared. And this signal is proportional to the coupling to the power of 4th. So we can convert, for example, we can draw 1 sigma contours in terms of the couplings for a given axion mass. And this is the formula for the CMB, for the temperature autocorrelation. but there are similar and slightly more complicated expressions also for the other observables that I mentioned. Let me just note these are just a bunch of formulas. I don't want to confuse you, but I just want to point out that different observables have different scalings with the coupling. And in particular, the cross correlation between temperature and galaxy fields has a scaling with the coupling squared. And this turns out to be a more favorable scaling of coupling as a function of the number of L modes. So the reason why this is a sensitive probe is that you have access to many angular scales, so you're summing over many L modes, and this is more advantageous for the cross-correlation observable, and this is the reason why this turns out to be the most powerful. But we're nevertheless showing here, just for completeness, the sensitivity for all the observables, also because in case that we measure a signal, then it is very powerful to have different channels that one could independently use to check a putative signal. So here I'm showing in the plane of axion coupling versus mass, our sensitivity projections using measurements from Planck. In dashed blue and orange, the CMB autocorrelation sensitivities for temperature and polarization, while we're also showing cross-correlation using, as an example, the unWISE galaxy catalog, which is an existing catalog that can be already used. So as I said, the green line is the most sensitive cross-correlation between temperature and galaxies. And here, as you might notice, the polarization observables have a shaded band around the central value. And this is an uncertainty given by the unknown magnetic field coherence length. So it's not due to the unknown size of the magnetic field, just the even more uncertain coherence length. And the same for a more futuristic CMB stage 4-like experiment. But there are also results that will come in between, like, as I said, from ACT or the Simon observatories that should be somewhere in between current Planck results and CMB-S4. So let me just say before concluding a couple of words regarding these other lines shown here, which are existing astrophysical bounds on axions. The first one here comes from axions that are produced in supernova 1987A and then can convert into X-rays within the magnetic field of our galaxy. And similarly around there, we also have bounds coming from X-ray observations for axions that are produced in stars and convert within the Milky Way magnetic field. The strongest bound shown here is instead coming from a very similar effect to what we're looking at here, but instead using the spectra, the X-ray spectra of quasars within clusters. So by analyzing the spectra, the authors of this paper look for deviations that could be induced by conversion of X-rays into axions. And there has been some debate in the literature because about the robustness of these bounds, because again, these are also, of course, very sensitive to the specific modeling of the magnetic field within the cluster. So because, as we also said before, most astrophysical searches are unfortunately affected by possible systematics due to the modeling of the magnetic field and unknown emission spectra. I think it's interesting to have complementary probes, and it is worth doing the analysis, even though we do not expect to be sensitive to orders of magnitude smaller couplings. Okay, let me just say, this is the final to last slide. I just want to explain what the future directions we're thinking about. First, we would like to extend this to smaller axion masses, and this is possible if we consider ambient electrons with a smaller number density. So in our calculation, we relied on semi-analytical modelings of the number density of the electrons, which are reliable only within the virial radius of halos. But we're thinking about using results from the simulations to expand this farther out in the outskirts of the halos that would allow us to access smaller masses. And also, it would be interesting to considering the limit of effectively massless axions, in which case there is no resonance conversion, but the conversion probability is still anisotropic because it depends on the negative fourth power of the plasma mass. So it is still sensitive to the distribution of the number density of electrons. And these are some preliminary results that, again, the student from Columbia University produced very recently. He already computed the observed cross-correlation between Planck and the unWISE galaxy catalogues, here shown in blue, at different L modes. And this seems to be roughly compatible with zero, so we think we can use these results to place a constraint on axions, an actual constraint. So to summarize, the take-home message here is that I think it's interesting to use existing and near future cosmological observations to test new physics in general. I've shown an example with the axions. There is a very similar phenomenon happening for dark photons. There could be similar signatures coming from, for example, a new dark radiation component or other perhaps new physics scenarios that we haven't yet thought about. And I want to acknowledge and thank my collaborators again. I will end here. I'm happy to take questions or comments. Thank you.
So thank you very much, Cristina, for this great talk. So questions for Cristina, please. Questions? Seems like everything was clear.
Either everything was very clear or it was totally not understandable.
So I do have another question. So there's this kind of scenarios in which axion-like particles acquire masses which are dependent upon the temperature of the environment.
Mm-hmm.
So you know, if particularly in these scenarios, as far as I understand, where you have like chameleon fields,
mm-hmm.
the axion mass becomes environmental dependent. So in those cases, as far as I understand, you won't be able to produce these states, say in stars, right?
Mm-hmm.
Or in supernovae. Okay.
I see.
If this is the case,
finite temperature correction to the
exactly. So if this is the case, if the axion-like particle mass becomes environmental dependent, how much that will impact the results that you have shown here? Can this kind of environmental effects be evaded in this scenario? I mean, in this kind of searches.
So I have to say, I'm not super familiar with these finite temperature effects. So I don't know exactly parametrically what is the magnitude of these effects. I would expect, though, that you would need, if I recall correctly, like these effects are important in quite high temperature, like as you said, in supernovae or other like hot environments, like in the early universe, perhaps. But here, because we're looking at conversion like in the circumgalactic medium, which is mostly, like there is a gas of charged particles, but it's not like a dense environment. of course, there are going to be objects, right? Like here and there are neutron stars and whatever, but these occupy a small fraction of the volume. So they shouldn't affect the magnitude of the signal very much, because when you're integrating over all the space, it is mostly cold. And so I don't expect those corrections to be important or to affect the signal significantly.
Okay. And you also mentioned that this the conversion happens for certain positions as a function of radius. You know, I consider a halo, so you have you maximize the conversion as a function of r, right? But that is a statement which is dependent upon the halo that you choose. So if rather than using an NFW halo, I use another one, then the position where this will take place will be different. How much that affects the quality, so to say, of the predictions that you are generating?
What is really important here is not the distribution of dark matter, but the distribution of the gas. And to model that, we use an analytic profile, which is called, from the author of the paper, the Battaglia profile, which has some parameters that depend on the halo mass and redshift. But yeah, it's a model, and we don't know, like, it is compatible with observations like from the KSZ or other effects that are sensitive to the electron density. But yeah, you can definitely ask the question, like, what happens if you change that profile? And we didn't do it in our paper, but I have a plot here from my collaborators that they checked this for the dark photon signal in two extreme scenarios. So here is a different parameter space because it's the dark photon coupling versus mass, and the different curves. The green curve is for the gas profile that we used, while the black would be for an NFW, so like a dark matter profile. And yeah, for heavier masses, there is a strong effect, but for most of the range, I think here there is just a rigid, like a vertical line, because they probably ignored the inner part of the NFW profile, which is very spiky. But within the bulk of the region, then this is the effect.
Yeah.
And
the
so
gas like kind of overlapping, right? A very good overlapping between both.
Yes, and the gas profile should really follow like the NFW. I think it's a pretty extreme variation from the gas profile.
Okay, so further questions for Cristina?
What is the reason why this gas and NFW profile are very similar in this in that range around 10 to the minus 13 and 10, a little bit larger than 10 to the minus 30?
So I think that the reason why you don't see a high sensitivity in the coupling is that these observables are proportional to like the autocorrelation is proportional to the coupling to the fourth, and the cross correlation to the coupling squared. So in the end, when you convert the curve in terms of the coupling, you're always taking square root of or power of the 1/4. So some uncertainties get reduced due to this scaling with coupling. And also because I think for the variation in the profile, how is this affecting the signal? Essentially, it means that the conversion happens at a slightly different scale. But yeah, depending on whether you can resolve or not this scale, I think the effect might not be that strong.
Thank you, Cristina.
No
Any
problem.
more questions for Cristina? So may I ask a last one?
Sure.
Yeah, okay. So
Yes, sure.
okay, so you have this so as you said, so different kind of scenarios or mechanisms that might contribute to CMB secondaries. So imagine we managed to get a measurement of this anisotropies. Can one tell whether this was produced by what you are analyzing or whether it was produced by dark photons? Is there a way to tell or to disentangle which mechanism is really responsible for that anisotropy?
Yes, the nice thing about axion and dark photons is that they have exactly the opposite scaling with frequency. So the axion is stronger for heavier frequencies, while the dark photon has a scaling as 1/frequency. So yeah, it just dominates in different frequency channels.
Okay.
And yeah, so you would be able to distinguish it, and also it means that you are competing with different what cosmologists call foreground contaminations, so different background levels, because at small frequencies you are primarily competing with synchrotron emissions. So that's what the dark photon is competing with, while at high frequencies you are competing with the CIB, the cosmic infrared background. So yeah, they should look different. Yeah, what is really hard, at least in my opinion, and just to be honest, is to distinguish it from other astrophysical effects like this foreground. Because it's true that you have a characteristic frequency dependence, but at the end of the day, Planck has a finite number of frequency channels, typically like 6 are the one that are actually important. And so even, yeah, with 6 channels, distinguishing a spectrum that goes like omega or omega squared can be hard. So
Okay, thank you, Cristina.
no problem. Thank you very much for having me.
Thank you so much, Cristina, for the very nice and very complete talk.
I hope to visit in person at some point.
That'll be great. Yeah, that will be great.
Yes, it would be nice.
Yeah, you're very welcome to visit. Yeah.
Here we also organize a biannual workshop in January, so it will be great if you can come in January. This high energy physics workshop.
This year in 2025, there is going to be again the conference in Valparaiso.
Exactly, 2025, something like the week of 10 of January.
I see. Yes, I participated in that conference, if it is the same conference, the last one in 2023.
Exactly, the same. Yes, this workshop of the high energy physics that is area will be the week of 6th of January, something like that.
Yeah. Okay, I'll keep it in mind.
Yeah. Okay. So thank you very much, Cristina. Yeah.
Thank you, and I'm sorry, Diego, that you had to listen to this talk again, but this time was more slow. I think I had more time, so hopefully it was more clear.
I mean, better for me, because in that way I could understand better what you are doing.
Yeah.
Try. So okay, so I got it better. Yeah. Okay. Thank you very much.
Bye bye. Have a good day.
Bye bye. Okay. You too. Bye bye. Thank you.
Bye bye. A nice time to you.
Bye bye.
Bye.